Hi everyone, we are excited to be sharing our projects and experiences with PostGIS at PostGIS Day this year. In this presentation, we will focus on PostGIS as spatial backbone for multi-tenant web applications. We will look at a couple of free software open source projects in the domains of conservation planning and the climate and environmental impacts of food supply chains. And we will focus on aspects of user experience, developer experience, and performance. After a brief introduction, we will dig into our two main case studies, our Marxan Cloud and LandGriffon projects. We will then summarize key points before opening the stage to questions from the audience. But first, a brief round of introductions. There will be four of us from the Vizzuality team presenting today. Alicia is a data engineer at Vizzuality. Alex is a software engineer in the backend team. Elena is a scientist in our science team. And finally, myself, Andrea, software engineer in the backend team too. Our mothership is Vizzuality, a change-driven design and technology agency. We work with leading organizations within the domains of biodiversity, conservation, climate emergency, and food supply chains, and our projects and products have a strong spatial component, so dealing with spatial data is a complex and exciting part of our daily work. Let's focus on Marxan Cloud first. We'll see first what Marxan Cloud is and how it works, and discuss friction points we addressed. We'll then show how we've used PostGIS to address these friction points, and briefly review the architecture of the platform and key performance considerations. Marxan Cloud is a web-based collaborative platform for conservation planning. In the past 2 years, we've built an opinionated workflow on top of a much older piece of software, the Marxan Solver, which is a portable C++ tool that performs optimization calculations using tabular data as input and output. Preparing data for the Marxan Solver used to involve quite custom GIS workflows, whereas our Marxan Cloud platform provides a unified user experience, a sort of go-to interface for conservation planners. How does Marxan Cloud work then? In a nutshell, given conservation aims and targets, such as we want to protect 30% of the species throughout this mountain range across these two countries, and given relevant constraints, for example, part of our planning area intersects with an existing protected area, and we also have human settlements, infrastructure, and economic interests that we wish to leave alone, what would be the best spatial setup for a new conservation area that allows to meet our targets? Now, please fasten your seatbelts as we speed through the platform's interface as we put together, so to speak, a planning scenario in the Galapagos archipelago. Here we can see our planning area around the archipelago neatly divided into a square grid, which is the spatial scaffolding for planning. Ultimately, we want to know about each of the items in the grid, whether they should be protected or not. As part of our setup, we might want to consider existing protected areas, which will then enable us to know which portions of the habitat of each species we should consider as already protected. Here we have highlighted in blue specific protected areas that fall within our planning area. To take into account constraints such as human activity, we use what we call a cost surface that assigns higher costs to planning units that would be more expensive to protect, for example, in terms of land purchase or resettlement costs. We can then upload and select features. These may be species or specific habitat types. Basically, features are anything we wish to protect. Here we have highlighted a couple of species and a couple of habitat types. For each feature, we can then set a conservation target as a percentage of the feature that we want to protect. And here we go. The platform has now processed our setup of targets, existing protected areas and constraints, and we can see that feature distributions are now looking more like an 8-bit video game where each pixel carries information about presence of one or more features. Before running the solver, a lot of tiny knobs can be tuned, but we won't be looking at them today. And finally, we can run the solver. At this stage, the platform synthesizes all the setup we've prepared so far into a handful of CSV files, which are then read when we execute a solver's binary. The solver will run its calculations a given amount of times. Let's say we've asked it to solve our scenario 100 times here. We wait for it to finish its calculations and then collect and parse its CSV output for these 100 solutions, and then we finally bring all the solution data back into the platform. And here we go. Here we have a selection frequency with pixels in bright light blue being those that have been selected in most of the 100 solutions proposed, and in darker and darker colors the pixels that have been excluded from most solutions. Maybe they were more expensive to protect, or there were no features that would be found there. Finally, we can see a summary of how targets may be achieved in each of the proposed solutions. Here all the targets will be met or exceeded. As a final screenshot, we show here the public view of the same project we've been working on. This is part of the collaborative aspect of the platform. And we're done with our conservation planning. In practice, this process would typically take months or longer, as there would be many stakeholders, improvements to input data, and so on to take into account. But we've been told from practitioners that Marxan Cloud does already remove most of the accidental complexity involved in dealing with the preparation and interpretation of Marxan analysis. So that's rewarding to know in terms of user friction. Now, on to development frictions. One of the friction points that we are dealing with is that users will need to run spatial calculations of widely varying complexity depending on the traits of each project. Likewise, as they tune their scenarios, users will want to see previews of their setup reflected on screen and to get a sense of how their tweaks affect results, all in near real time. Adding to the frictions, this is a multi-tenant platform, which means we need to combine unpredictable loads for each single tenant into a kind of higher order unpredictable load for the platform as a whole. And last but not least, developer experience was a core concern for our team. We wanted to use tools and frameworks that help us keep accidental complexity as low as possible. Alicia will now go through key points of our use of PostGIS in the Marxan Cloud platform.
Thank you very much, Andrea. So let's talk about PostGIS in Marxan Cloud. We're going to go over the different flows and how PostGIS has enabled them. Let's first talk about how data is ingested into the platform and how it is stored in the database. Whenever spatial data is ingested, either platform-wide data through ETL pipelines or user-supplied data from shapefiles, we take some steps to optimize data storage for best performance of the analytical queries that we run over the platform. In our case, this typically involves repairing geometries, applying relevant simplifications, and splitting multi-polygon geometries into individual polygons. We also store the geometries data within our column table and compress. This is because we have traded storage space and I/O bandwidth for CPU time, both on write and on query. Spatial regular grids based on selected area in Marxan are the backbone for the spatial analysis and later for the Marxan solver. We are using the functions that latest version of PostGIS provides in order of generating them. Also, we allow users to unlock their custom grids, which we validate. Now let's talk about the spatial analysis that we perform with the data in Marxan platform. We make use of spatial filtering, spatial intersections and area calculations as our main analysis. As you could see here, one of the analyses that we perform is in order to check if a planning unit is already protected or not. This is done through a calculation of area proportion for the planning unit, and later we let users to configure within a threshold if the planning unit is going to be protected or not. Later, this is also used to calculate the presence or absence of each feature within each planning unit and to calculate how much of each planning unit intersects with each feature. Likewise, these intersections and area calculations allow users to know what are the status quo look like, given their targets they have in mind. And again, in order to show how targets have been met, if at all. Sometimes there is no way to reach targets for some features given all the constraints. In which case planners discuss things, go back to the whiteboard, tweak things, and go through the flow again and again until they are happy with the results. Another example of how PostGIS help us build some functionalities within the Marxan platforms are boundary lengths. In order to help the Marxan solvers to calculate the connectedness of solutions, basically how clumped or scattered they are, and how much more a clumped solution may cost over more scattered ones, we calculate the pairwise boundary length of each couple of grid elements. Clumped solutions, as you can see on the image, are in general preferable because they are, again, in general, easier to manage, though they may be more costly. Here there is another example of the use of PostGIS through the platform. Within our maps, we make use of vector tiles that are produced directly by PostGIS through custom queries and prepared statements. We do also apply simplification to the displayed geometries depending on the sublevel. Here, there is an example on how we let users look at the features when they are configuring them, allowing them to turn on and off the vector layers that comes directly from the database. Also, once the Marxan solver is done with calculations, vector tiles from database still help us plot meaningful representation of the recommended solutions. There is one last interesting bit we wanted to show to you, that is the social component of the platform. We let users make a copy of public projects such as the one that we are seeing here and work on it independently with their own private dashboards. In order to do so, we keep a compressed archive of each published project that includes a bunch of tabular data, metadata, and the spatial data through the extended well-known binaries, and later is ingested back when the user copies it. It is all as fast as it can be since there is no fiddling with spatial data, no serialization, no overhead. The native binary representation comes out and it goes back in straight as it is.
As we approach some general considerations, let's look briefly at the architecture of the platform. Remember, this is a multi-tenant SaaS platform with a quite common load profile. Most of the time it just sits there idle. Occasionally some users may go and have a look at public projects. Maybe a journalist will link to a project and there will be a flurry of visits. Although by then most of the data served to visitors will be cached and involve no calculations at all. And then we expect occasional spikes when people are being trained on the use of the platform, and suddenly there may be a few tens of students or practitioners running spatial analysis all at the same time. Here we see a bird's view of the Marxan Cloud architecture, a single page app interacting with the backend that runs on a Kubernetes cluster, plus two managed PostgreSQL databases. One of the two Postgres databases handles mostly metadata, while the other one may be considered as geospatial microservice. This is where all the PostGIS action happens. This split database setup is one of the possible ways to isolate resource-intensive spatial computations.
Let's talk about performance. Given the expected load profiles and the concrete architecture of the platform, how do we reason about performance envelope bottlenecks? Well, the worst case scenario that we dealt is when tens of users cause a spike of concurrent spatial computations. We do optimize all we could and accepted that in some cases things may slow down a bit because of disk I/O contention within a single PostGIS node. We also make broad use of pre-calculated hashes to avoid performing spatial intersections while users are tweaking their scenarios, and all that they change is tabular data, or to allow to share geometries between different scenarios for a single user without duplicating data or computations. At some point in the future, we may need to think about removing non-bottlenecks, and likely others we don't even know of yet. We have briefly considered sharding spatial data by tenant or by some other relevant criteria, using Citus or other solutions that can allow to scale the platform horizontally. But again, we have not hit this wall yet. Now, over to Elena and Alex, who will introduce our LandGriffon project.
Okay, so now Alex and I are going to talk about another project where we are using PostGIS for supply chain impact analysis, which is called LandGriffon. In this part of the presentation, first we are going to provide you with a description of LandGriffon and its main functionalities. Then we will explain why we have decided to use H3 with PostgreSQL and PostGIS for this specific project. And finally, we will end up with some challenges and opportunities that we have found along the way. What is LandGriffon? LandGriffon is a platform that we are building to help companies to enhance transparency into their material supply chain to point of origin. Here in the slide, we have some of the main key features, as can be a spatial sourcing model for supply chain mapping, calculation of impacts and risks for different environmental and social indicators, and a scenario planning tool to identify different pathways and strategies to reduce risk and impacts over time. The platform is based on 4 different parts. First, the users have to import the procurement company data. As a minimum, we will need the information of the materials and the volume that the company is buying and the information they have regarding the sourcing location. Then, using this information, we geolocate the different suppliers based on a location type, which are the ones that we have under the point 2. For example, a farm location, a region, or a country of production. This geolocation will be done using a probabilistic sourcing model, which I will explain in more detail in the following slide. During the same data ingestion, we will be calculating the associated impacts, environmental impacts, which have divided between farm level and landscape level indicators. Finally, once we have all the supply chain mapping and the different impacts calculated, the user can explore different pathways to reduce these impacts by, for example, working with producers and suppliers to reduce risk, change product formula, or source from more sustainable locations. At the core of LandGriffon, we have the probabilistic sourcing model. This sourcing model basically geolocates the procurement data and identifies the areas in which the raw materials are likely to be sourced from. As the information that companies have on the production of these raw materials will vary in detail, this geolocation will be based on a defined location type, which are the ones that I have presented in the previous slide. This location type determines, for example, if the company knows the exact location of the production farm and therefore the output will be a point on a map or nothing at all. So we will be using trade statistics to obtain a weighted map. The ingestion of all of this information is done using an Excel file as the one that you can see in this slide. During the same ingestion, LandGriffon calculates indicators of environmental impacts such as the water use, land use, or greenhouse gas emissions. These indicators are calculated by combining the previously geolocated company data with different global datasets. Based on all of this, we can conclude that LandGriffon performs impact calculations automatically on imported data, but also during the generation of different scenarios and projections. At the same time, LandGriffon provides tools such as the ones that we have here on the slide for visual and quantitative analysis, export, and simulate changes in impacts. So we have to carefully think about how to perform all these calculations. In some previous projects, supply chain projects, we directly use raster data and vector data to perform summary statistics at database level. However, we found some difficulties using this approach, mainly due to raster preprocessing requirements, as can be issues with resolution and precision, spatial transformation to match projections use, which reduced performance in calculations, especially in the creation of new scenarios. For this particular project, we decided to change this approach and try H3 with PostgreSQL and PostGIS. H3 is a geospatial index system that partitions the world into hexagonal cells, as you can see in the sample image in this slide. Every position in the world has then a cell identifier associated with it. H3 indexes refer to cells by the spatial hierarchy. This means that every hexagonal cell up to the maximum resolution supported by H3 has 7 child cells below in this hierarchy. Essentially, the use of H3 will allow us to get some of the benefits of raster maths in terms of speed and memory usage with lower distortion and nicer looking visualizations. There are some drawbacks though, but I'm going to let Alex explain all of this in more detail.
All right. So The most prominent benefit of H3 is that spatial data becomes indexed, allowing easy joins with other datasets, fast filtering, aggregation, grouping by operations, and mostly any native SQL magic you can think of, and overall provides quite neat visualizations. As for the drawbacks, we have seen that the base library we are using for PostGIS is still a bit limited, allowing you conversions only from geometries to H3 and the other way around. However, it does provide quite useful features to work with the indexes, as getting parents or children given some index, so allowing you to be able to get lower or higher resolutions from the ones you have stored in your database. We have also seen some errors transforming from raster to H3, as the index only gets the value that is in the centroid of the raster, so some resampling is needed here. How do we work with H3 in LandGriffon? So we have mainly two data sources, what we call the seed process and the user data. The seed process is ingesting the data that is part of the core system and required for minimal platform usage. We ingest a variety of different datasets, for example, global biodiversity loss data, production or harvesting data for different materials, and those can come on different formats. So some pre-processing is done, as the one mentioned earlier, to finally store it as H3 indexes in the database. We use this master H3 data table to keep track of these datasets and the ones that can be ingested later on. This allows us to be quite flexible in terms of the shape this data can have, and remodeling of the data model is not needed. As for the user data ingestion, as Elena mentioned, a user can provide a location or locations where a material or several materials are bought from. We need to geolocate this information to be able to calculate the impact associated with it. So let's see a simplified version where PostGIS comes handy here. A location can come in different formats, like as coordinates or as an address, for example, depending on the location type. So from this information, we will get a point, and we will use this point to intersect it with other geometries we have previously ingested to determine the most accurate administrative region this location belongs to, as well as perform some other geovalidations. Again, depending on the location type, we might want it to store this new location as a point or as a radius around this point or whatever. And then finally, we transfer this new geometry of this new location to a set of H3 indexes. So at this point, we can efficiently join those indexes of this new location to different datasets to perform some computations over it, aggregation, subtraction, whatever we need, and serve the resulting data in a key value format, the key being the index itself and some value associated to it. So in the example of the image, we have retrieved carbon emission data related to palm oil production in Aceh, Indonesia. There are some challenges and opportunities we are facing. As we mentioned before, storing multiple resolutions might not be needed, as you can always increase or decrease the resolution, but this can become very tricky depending on the size of the region. So for example, in resolution 1, you need 55 hexagons to cover Russia, but in resolution 9, you need 145 million hexagons, increasing exponentially for each level. And for example, increasing resolution from 6 to 9 on the fly can take minutes to complete. So for now on, that's the biggest challenge we are facing, dealing with lots of data on high resolution. Right now, we work with a maximum resolution of 6, which can be decreased if we are serving a global map, or be more accurate if we are filtering by some location. However, in order to be able to work with higher resolutions and provide more accurate data, we will need at some point to most likely develop an H3 tiler, which will allow us to serve hexagons that are within the viewport, reducing drastically the number of hexagons needed to cover the location on a higher resolution as we are zooming in. But overall, yeah, we have seen huge wins, especially performance-wise, as data size is growing. And that's it. Thank you.
Okay, so let's wrap up with a brief final summary, going through some key traits of the PostGIS advantage. Using PostGIS rather than, for example, one of the many Python libraries and frameworks to work with spatial data has allowed us to embed computations in the data layer itself. This can be debatable in general and might come with trade-offs, but in our case, it made sense to consider the PostGIS server as one of the microservices in the architecture, which happens to have data at hand to do its job. The PostGIS API is also a joy to work with. Elegant, efficient, and solid, it does its job and stays out of the way. Moreover, we see PostGIS as a sort of lingua franca. As we use it through more and more projects, the science and backend teams at Vizzuality have become more familiar and proficient with it. And onboarding new engineers to our project means helping them become conversant mainly with a single API, the one of PostGIS, rather than a range of tools and frameworks. We do, of course, use other tools too for very specific tasks, but PostGIS is indeed a language that everyone speaks. What are we still missing then? In general, we've been treating PostGIS computations as a sort of black box. We tell it what we want, we let it crunch data for as long as needed, and we know that it will come up with good responses at some point. We currently don't know how long the wait will be, so we just ask users to wait patiently. And as we mentioned earlier, a time will come when we'll feel the need to shard data to provide some isolation of spatial computations. But that's an architectural change that is in large part transparent to PostGIS, and we'll get there once we need that. And that's it. Thank you so much on behalf of the whole Vizzuality crew.